Hello everyone, welcome back. So today we will cover the Galois Contest of 2026. So here for question 1, we have that a prime number is a positive integer greater than 1 whose only positive divisors are 1 and itself. For example, 2 is a prime number since it is greater than 1 and its only positive divisors are 1 and 2. What is the product of the three smallest prime numbers? So this is fairly straightforward. The sieve method, or you can just know the prime numbers. There are 2, 3, and 5, so their product is equal to 30. And this fancy pi sign is just product. Next for b, we have there are two integers c with 1 less than or equal to c less than or equal to 20, for which c minus 3 over 4 is a prime number. What are these two possible values of the integer c? So since this is prime, which is an integer, we know that c minus 3 is a multiple of 4. So this gives us c is equal to 3, 7, 11, 15, and 19. So now plugging this into this gives us c minus 3 over 4 is equal to 0, 1, 2, 3, and 4 respectively. So the only two primes here are 2 and 3, so this means that c is 11 and 15. Now for part c, we want all integers d with 1 less than or equal to d less than or equal to 10, for which 21d minus 77 is a prime number. So the key idea here is to notice that we can factor out a 7. So this is 7 times 3d minus 11. Since this is prime, we know primes only have two divisors, so this means that 3d minus 11 will be equal to 1. And this gives us d equals 4. And so this is the only solution. For number 2, we know that triangle ABC has vertices 3, 4, 2, 1, and 6, 1, and we want to find its area. So using the formula half times base times height, we see that B is 2, 1 and C is 6, 1, so the base is 4. A is 3, 4, so the height is 3. So now, plugging these in, we have the area as half times 4 times 3, which is 6. For part B, we know that point D is the image of point B after it is reflected in the y-axis. So point D will be here. And we want the area of triangle ADC. So after reflection, we can calculate the coordinates to be -2, 1. So now, instead of the base being 4, the base is 6 minus -2, which is 8. So now using the same formula, we have half times 8 times 3, which is 12. For part C, point E is the image of point A after it is reflected in the horizontal line y equals -2. So let's erase this to make some space. And so after reflection, A will go here, so this will be E. So now, the base is still 4, but the height has changed. And so since we're flexing in y equals -2, then we see that E must be -8. negative 9. So now when we calculate the area, we have half times base, which is still 4, times height, which is 9. And so this area will be 18. Finally, for part D, point F is the image of point A after it is reflected in the horizontal line y equals k. Determine the two different values of k for which the area of FBC is equal to 12. So essentially here, for the area of FBC to be equal to 12, if we use the same formula, half times base, which is 4, times height is equal to 12. So this means height equals 6. This can go either up or down, so we know that F is either equal to 3, 7 or 3, negative 5. So now to calculate the line in which this is reflected, we can take the midpoint between A and F. So for 3, 7, the midpoint is 7 plus 4 over 2, which is 11 over 2. And for negative 5, it's negative 5 plus 4 over 2, which is negative 1 over 2. And the reasoning is, since A and F are collinear in the straight up, if we have a line in the middle which passes through the midpoint, then that's the line that they're reflected over. So our answer will be 11 over 2 and negative 1 over 2. So now we have problem 3. For every positive integer a, the units digit of a squared, a cubed, and so on will form a repeating sequence. In each sequence, the smallest number of consecutive units digits that repeat consecutively and indefinitely is at most 4. This number is called the cycle length. For example, when a equals 3, the sequence is 3, 9, 7, 1, and so on. For a, what is the unit digit of 3 to the power of 43? So since we know that this repeats every 4 numbers, we just need to find the remainder when 43 is divided by 4. 43 is equal to 4 times 10 plus 3. So after 10 cycles, it will go 1, 2, 3. And so the answer will be 7. For B, we want the number of integers j for which 4 to the j plus 8 to the j is a multiple of 10. So here we can look at the digits. For 4, it goes 4, 6, and repeats. While for 8, it goes 8, 4, 2, 6, and then it repeats. So now since for every multiple of 4 for j, it goes back to 1, since it's multiplied by 1, then we just need to figure out how many of these become a multiple of 10. So when j is 1 more than a multiple of 4, this is 4 plus 8, which is 2. When j is 2 more, it's 0. When it's 3 more, it's 6. And when it's 4 more, it's also 2. So it only works if j is 2 more than a multiple of 4. So we know that 2024 is equal to 4 times 506, with 2 more remaining. So now this means that there's 506 plus 1 possibilities for j, which is 507. Now for C, we want to determine the number of integers k with 1 less than or equal to k less than or equal to 50, for which 2 to the power of k plus 3 to the power of k has the same unit digit as 8 to the power of 2026k plus 9 to the power of 2026k. So here we can use the same strategy. The pattern for 2 is 2, 4, 8, 6. And the pattern for 3 is 3, 9, 7, 1. So their sum has a pattern of 5, 3, 5, 7. Now we consider 8 to the power of 2026k and 9 to the power of 2026k. So if k is odd, then we have 2026k will be 2 more than a multiple of 4. So since the pattern for 8 is 8, 4, 2, 6, when we have 8 to the power of 2026k, then the pattern becomes 4, 6, 4, 6. Since it essentially skips the odd numbers. For 9, it's slightly different because we can rewrite this as 3 to the power of 2 to the power of 2026k, which can be rewritten as 3 to the power of 4 to the power of 1013k. 3 to the power of 4 is 81, which has a unit digit of 1. So this pattern will always have a unit digit of 1, since 1 to the power of anything is itself. So now we know both these patterns. So when we add them, 4, 6, 4, 6 plus 1, 1, 1, 1, we get 5, 7, 5, 7. So this means that out of every 4 numbers, 3 of them work for k. So now we find how many cycles there are in 50. So this is 4 times 12 plus 2. So here we will get 12 cycles of 3 each, plus 1 more in the 2 that's left over, since the 2 that's left over is the first 2. So here we have the answer, which is 37. Now for 4a, we know that the set R contains the points 0, 0, 0, 1, 0, 4, 0, 9, 0, 16, and 0, 25. The midpoint of every pair is plotted on the xy plane. What is the number of distinct points that are plotted? So first we need to count how many points are plotted. So there are 6 points here, so we need to choose 2 of them to find the midpoint. So we have 6 choose 2, which is 15. However, we need to subtract 1 for the midpoint 0, 25, 2. Since this is both half of 0, 0 plus 0, 25, as well as half of 0, 9 plus 0, 16. So now we have one duplicate, so when we subtract this, we get 14 distinct midpoints. Now for B, the set S contains exactly 20 distinct points, each of the form n, n plus 2, where n is an integer, and 1 is less than or equal to n less than or equal to 20. The midpoint of every pair of distinct points from S is plotted on the xy plane. Determine the number of distinct points that are plotted. So, since they're of the form n, n plus 2, we know that they form a straight line and the points are evenly spaced along this diagonal. So this means that we have 2 possibilities. Either the midpoint is a lattice point, meaning each of its coordinates is an integer, or the midpoint is between 2 lattice points. So together, what this means is that out of the 20 points. There are 20 of these points that are lattice points, plus the 19 midpoints between them. Now all we need to do is subtract the ones that can't be midpoints, which are the ones on the edge. So we subtract 2 to get 37. Finally, for C, a set T contains exactly 100 points having distinct y-coordinates. The midpoint of every pair of distinct points from T is plotted on the xy plane. Determine M, the minimum number of distinct points that could be plotted. So first, we claim that the answer is 197, and we will give a construction. So by having them equally spaced, such as the example in part B, we have 100 points here, 100 points, plus the 99 points between them equally spaced. And finally, we subtract the 2 points on the edges, since they can't be the midpoints, to get 197. So for example, if we pick this point in the middle, then these 2 points will get that midpoint. And if we pick this point, we can pick the 2 points on either side of it. So now we need to prove that this is in fact the minimum. So since we know that they are distinct y-coordinates, we know that first we can sort them. So let's let y1 be less than y2 and so on until y100. So now if we consider the midpoints of the y-coordinates, then we know y1 plus y2 over 2 is less than y1 plus y3 over 2, which is less than y2 plus y3 over 2, and so on. So we increase one variable at a time until we get y98 plus y100 over 2 less than y99 plus y100 over 2. So these inequalities are true because of our ordering and because they're distinct. And this already gives us